Hi there and welcome. We're looking at section 2.6 today. I'm Rebecca Weaver. We're going to be doing some more optimization problems. So we're going to be looking at some more examples of optimization. We're going to still do our same procedures, just a few more problems. Our first example, it's on an economic order quantity. We're looking at inventory control. A bookstore is attempting to determine the economic order quantity, EOQ, for a popular book. The store sells 8,000 copies of this book a year. The store figures that it costs about $40 to process each new order of books. The carrying cost due primarily to interest payments is $2 per book, to be figured on the maximum inventory during an pre-order period. How many times a year should orders be placed? Now, the quantity that we want to be minimizing, of course, is cost. Therefore, our objective equation is going to contain a variable representing the cost. Let X be the order quantity, and let's let R be the number of orders placed throughout the year. Inventory cost equals ordering cost plus carrying costs. This is going to be our objective equation. We're going to have cost equals 40R plus 2X. So we now need to determine the constraint equation. The only piece of information we've not yet used in some way is that the total number of books that will be ordered for the year is 8,000. Using this, we create a constraint equation as follows. 8,000 equals R times X. Now we're going to rewrite that constraint equation just like we always do, isolating one of the variables. We're going to say R equals. We could do either one, but we're going to do R equals. Now we're going to rewrite the objective equation using the substitution that we just acquired from the constraint. So here's our objective. Substituting back in, we're going to get that cost equals 320,000 over X plus 2X. Now we're going to use this equation to sketch a graph. So we've graphed that function. Minimum, because that's what we're looking at, minimizing costs. Somewhere in here, I think this right in here is lower than that, but we'll see for sure. How are we going to know? Well, it appears from the graph there's exactly one relative extremum, relative minimum around x equal 400, which is where we thought. To know exactly where this relative minimum is, we need to set the first derivative equal to 0 and solve, since at this point the function will have a slope of 0. So we write down our cost equation and we take our derivative. That's going to be negative 320,000 over x squared plus 2. Set that equal to 0. Then we're going to solve it for x. What we'll end up with is that x equals positive negative 400, but of course we're not going to take negative 400 because that wouldn't make sense. So we will take x equal 400. Now we know that the cost to be minimized when x equals 400. So we're going to use the constraint equation now to determine our value of R. We're just going to plug that into 8,000 equals R times 400. Solve for R, and we get that R is 20. So the values that are going to minimize cost are x equals 400 books per order and R equals 20 shipments of books per year. Very nice. Next, we're going to use another example. We're going to look at revenue. Shakespeare's Pizza sells 1,000 large veggie pizzas per week for $18 pizza. When the owner offers a $5 discount, the weekly sales increase to $1,500. That's a lot. Assume a linear relationship between the weekly sales, A of X, and the discount X. We need to find A of X. Then what we're going to do is find the value of X that maximizes the weekly revenue. Now they give us a little hint to this. Revenue equals A of X times price. So since A of X represents the number of weekly sales and X represents the discount, the formula for A of X is going to be determined by doing the following. First, we notice that as X increases, so does A of X. Also, we notice that the basic number of weekly sales is 1,000, and that when the discount increases to $5, the number of sales increases to 500. Therefore, the desired function is a of x equals 1,000 plus 100 times x. So remembering that the discount is x and a of x is our weekly sales amount. To find the value of x that maximizes the weekly revenue, we must first determine a function for revenue. Well, that's just going to be revenue is our weekly sales times price. So we know our weekly sales function. So now we're going to determine the constraint equation. The only piece of information we've not yet used in some way is that the non-discounted price of pizzas is $18. Using this, we create a constraint equation as follows. Price equals 18 minus x. Now we're going to rewrite the objective equation using the substitution that we just acquired from the constraint. Plugging that in, we have our objective equation, plugging in for p, which is 18 minus x. We're going to simplify, and what we get is that revenue is negative 100x squared plus 800x plus 18,000. We're going to use this to sketch a graph of the function, and since x and r can't be negative, we're just going to look at the first quadrant. So here we have our function. Notice where our maximum is, somewhere right around in here. Pretty nifty. Appears from the graph there's exactly one relative extremum, a relative maximum around x equal $5. To know exactly where this relative maximum is, we need to first set the derivative equal to 0 and solve, since at this point the function will have a slope of 0. So here's our revenue equation. Take the derivative. We'll have negative 200x plus 800, set it equal to 0, solve for x, and we get that x equals 4. Therefore, we know that the revenue will be maximized when x is 4. That is, revenue will be maximized with a $4 discount, yielding a weekly revenue of $19,600. Let's look at another example. This one is of area of an athletic field. Now, an athletic field consists of a rectangular region and then a semicircular region at each end. The perimeter will be used for a 440-yard track. Find the possible value for x for which the area of the rectangular region is as large as possible. So what we're going to do is we're going to be maximizing area, namely the area of the rectangular region. Therefore, our objective equation will contain a variable representing the area A. So if we look at that area, we see the area is just x times h. All right. Now we're going to determine the constraint equation. The only piece of information we've not yet used in some way is that the perimeter of the track is 440 yards. We're going to, using this, we're going to create a constraint equation. The distance around the track is going to equal the lengths of the sides of the rectangles and then the lengths of the semicircles. So we're going to use circumference and to get that semicircle part there. Before we simplify the equation, it's worth noticing that the lengths of the semicircles is simply a pair of semicircles that, when put together, would form a complete circle. Therefore, this quantity would be the circumference of the circle, for which circumference equals pi times diameter, such that d is the diameter. And I see that 440 is going to be h plus h, the sides of the rectangles, plus pi times the diameter. All right, and that diameter is, we're going to say x. So we have 440 is 2h plus pi times x. That's our constraint equation. Now we're going to rewrite the constraint equation isolating one of the variables. We do whichever one we think would be the easiest. So we look at this thing and we say, I think it'd be easiest to make it read h equals. So that's what we do, make it read h equals. And we have h equals 220 minus pi x over 2. Now we're going to rewrite the objective equation using the substitution we just acquired from the constraint equation. So we take our objective equation, a equals x times h, substitute in for h, and we have a equals x times the quantity 220 minus pi x over 2. We're going to simplify this. Area equals 220x minus pi x squared over 2. We're going to use this to sketch a graph of the function, and we're going to notice that we get a maximum somewhere. This is a parabola. Looks like right here in the middle at 75 is what it looks like to me for a maximum. It appears from the graph that there's exactly one relative extremum, relative maximum somewhere around x equals 75. To know exactly where it is, we're going to set the derivative equal to 0 and solve, since at this point the function will have a slope of 0. All right, so we take our function, take the derivative, a prime is 220 minus pi times x, set this thing equal to 0, solve it for x, and we get that x equals 220 over pi, which is about 70. Therefore, we know that the area of the rectangular region will be maximized when x is 70 yards. All right. If you have any questions, be sure and email me, rweaver10@alaska.edu, and you have a wonderful day. Thank you for listening.